Ever wonder what it feels like to float through the universe's most beautiful spaces? Nebulae are basically cosmic hot tubs where stars are born, galaxies spinning like celestial carousels. Ready to explore the deepest, darkest parts of space with me? Don't worry, I'll be gentle with the mind-blowing facts. Stay close, stargazer. Welcome to another peaceful journey through the cosmos. Tonight, we'll drift gently through the ethereal beauty of deep space, exploring the serene wonders of nebulae and galaxies. As you relax and prepare for sleep, allow your mind to float freely among these distant cosmic clouds. Nebulae are perhaps the most visually enchanting objects in our night sky. The word nebula comes from the Latin word for cloud or mist, a fitting description for these delicate cosmic formations. When we look at nebulae, we're seeing vast regions of gas and dust suspended in the emptiness of space, some spanning hundreds of light years across. Despite their immense size, nebulae contain matter so diffuse that if you were somehow able to fly through one, you might not even notice you were passing through anything at all. These celestial clouds come in various forms, each with its own peaceful character. Emission nebulae glow with their own light, energized by nearby stars that excite the gases within them. The hydrogen atoms, most abundant in the universe, absorb energy from these stars and then release it as a soft, reddish glow that dominates many of the most famous nebulae in our sky. Oxygen, less common but still present, contributes gentle blue and green hues to the cosmic palette. Reflection. Nebulae, by contrast, don't emit their own light. Instead, they contain cosmic dust, tiny particles of carbon, silicon, and other elements that reflect the light of nearby stars, like a soft, diffused lampshade might scatter light in a darkened room. These nebulae often appear in soothing blue tones, as the dust particles scatter blue light more efficiently than red, the same process that gives our Earth's daytime sky its peaceful azure color. Then there are the dark nebulae, shadowy regions where abundant cosmic dust blocks the light from background stars and other nebulae. These create striking silhouettes against brighter backgrounds, like the famous Horsehead Nebula in the constellation Orion. The Horsehead stands in quiet contrast against a background of glowing hydrogen gas, its distinctive shape formed by the patient sculpting of radiation and stellar winds over countless millennia. Planetary nebulae form yet another category, despite having nothing to do with planets. These are the gentle final breaths of stars like our Sun, which, at the end of their lives, shed their outer layers in expanding, often symmetrical shells of gas. The name came from early astronomers who thought their round shapes resembled planets in their telescopes. Each planetary nebula is unique, with names that reflect their appearance: the Ring Nebula, the Cat's Eye Nebula, the Butterfly Nebula. Cosmic artworks painted in the soft glow of ionized gases. Among the most famous of all nebulae is the Orion Nebula, visible even to the naked eye as a fuzzy star in the Sword of Orion. Through a telescope, this region reveals itself as a swirling cauldron of gas and dust, illuminated by hot, young stars born within its depths. At about 1/500 light-years away, the Orion Nebula spans roughly 24 light-years and contains enough matter to make 2,000 stars the size of our Sun. Yet this massive cosmic cloud would be virtually invisible if we could somehow travel inside it. Its matter is spread so thin that it would be less substantial than the most delicate morning mist on Earth. The Eagle Nebula, made famous by the Hubble Space Telescope's Pillars of Creation image, offers another serene vista of cosmic beauty. These towering columns of gas and dust, each several light-years tall, stand with quiet dignity against the backdrop of space. Within these pillars, new stars are slowly forming, their gravity gradually pulling in more and more material. The pillars themselves are being eroded away by intense radiation from nearby stars, sculpting them like cosmic monuments weathered by time. Perhaps most hauntingly beautiful is the Horsehead Nebula, a dark cloud silhouetted against the soft glow of hydrogen gas in the constellation Orion. This distinctive shape, reminiscent of a knight's chess piece or a horse's head, emerges from the cosmic darkness with quiet elegance. The nebula stands about 1,500 light-years from Earth, its form created by the complex interplay of gravity, radiation, and magnetic fields that shape all nebulae. As you breathe deeply and feel the gentle weight of relaxation spreading through your body, consider that the atoms in that very breath, the oxygen, nitrogen, and carbon, were once part of ancient nebulae. These cosmic clouds are not just distant wonders to be observed, but part of the continuous cycle of matter that connects everything in our universe. The iron in your blood, the calcium in your bones, all were forged in the hearts of stars and scattered into space when those stars died, becoming part of nebulae before eventually finding their way to our small blue planet. In the vastness of space, nebulae remind us of the delicate balance between creation and dissolution, between form and formlessness. Their shapes constantly change, though on timescales far beyond human perception. If we could watch a nebula over millions of years, it would swirl and shift like smoke in a gentle breeze, parts of it condensing to form new stars, other parts gradually dissipating back into the void. As your thoughts drift among these cosmic clouds, allow yourself to feel the profound peace that comes from connecting with something so much larger than yourself, so much more enduring than daily concerns. The quiet persistence of nebulae, slowly evolving over millions of years, offers a perspective that can soothe even the most troubled mind. As we continue our peaceful journey through the cosmos, let's drift gently into the realm of stellar nurseries, the quiet, patient places where stars are born from the cosmic dust and gas of nebulae. These vast molecular clouds serve as the birthplaces of stars, regions where the building blocks of stellar formation gather and slowly, over millions of years, coalesce into the luminous objects that fill our night sky. Within the cool, dark recesses of molecular clouds, far from the disruptive energies of existing stars, hydrogen gas molecules and tiny dust particles float in a delicate dance of gravity and pressure. These clouds maintain temperatures just above absolute zero, chilled to around -440 °F, creating the perfect conditions for the patient process of star formation to begin. In this profound cosmic quiet, gravity begins its gentle work. Imagine a slight increase in density within one region of a nebula, perhaps caused by the shock wave from a distant supernova, or simply by the random motion of particles over time. This subtle increase allows gravity to gain a slight advantage. Ever so slowly, this region begins to pull in more material from its surroundings. As matter accumulates, the gravitational pull strengthens further, drawing in yet more gas and dust in a self-reinforcing cycle. Over thousands of years, this process continues in profound silence, building what astronomers call a dense core or protostar, the embryonic beginning of a stellar life. As material falls inward, its gravitational potential energy converts to heat, gradually warming the core. The developing protostar begins to glow, though not yet through nuclear fusion, but simply from the conversion of gravitational energy to thermal energy. Like how a comforter warms you not by generating heat, but by trapping what's already there. The most famous stellar nursery is perhaps the Orion Nebula, visible even to the naked eye as a fuzzy patch in the constellation Orion's sword. Through telescopes, we see a swirling tapestry of gas illuminated by the hot young stars already born within it. At its heart lies the trapezium cluster, a group of infant stars less than 1 million years old, mere babies in cosmic terms. These youngsters flood their surroundings with energetic light, causing the nebula's hydrogen gas to glow with a soft, rosy hue. Another remarkable stellar nursery is found in the Eagle Nebula, specifically in the region known as the Pillars of Creation. These towering columns of gas and dust, standing like silent sentinels against the backdrop of space, harbor numerous stellar embryos within their opaque folds. The pillars themselves are slowly being eroded by the radiation from nearby stars, in a delicate balance between creation and dissolution. Within these pillars, astronomers have observed what they call evaporating gaseous globules, or eggs, small, dense cocoons of gas that are in the process of collapsing to form stars. Each egg contains roughly the mass of our Sun, concentrated into a space not much larger than our solar system. Inside these protective envelopes, new stars take form, shielded from external disruptions as they slowly gather their strength. The process of stellar birth follows a pattern of gentle balance. As a protostar continues to contract under gravity's patient pull, its core grows increasingly hot and dense. When the temperature reaches about 10 million degrees Celsius, something miraculous occurs. Hydrogen nuclei begin to overcome their mutual repulsion and fuse together to form helium. This nuclear fusion releases energy, creating an outward pressure that finally balances the inward pull of gravity. At this delicate equilibrium point, a true star is born, beginning its long, steady shine across the cosmos. Not all the material in a nebula ends up forming stars. In fact, the process is remarkably inefficient by human standards, with only about 10% of a nebula's mass typically converting to stars. The remainder is gradually blown away by stellar winds, streams of charged particles flowing outward from the newly formed stars, and by the intense radiation these young stars produce. This gentle clearing creates beautiful structures like bubbles and cavities within nebulae, visible in many Hubble Space Telescope images that show the interplay between new stars and their birthing clouds. The leftover material isn't wasted. Some of it will drift away to potentially become part of other star-forming regions. Some will remain in orbit around the new stars, eventually cooling and condensing to form planets, moons, asteroids, and comets. Our own solar system formed this way about 4.6 billion years ago, from the leftovers of a stellar nursery long since dispersed. In the Eagle Nebula's Pillars of Creation, this process unfolds with particular beauty. The pillars themselves, each several light-years tall, contain enough material to make countless new solar systems. Their edges are being slowly shaped by the radiation and stellar winds from nearby stars, creating the distinctive pillar forms. Within their dense interiors, protected from external disruptions, new stars slowly gather mass and energy. What makes stellar nurseries so conducive to relaxation is not just their beauty, but the timescales on which they operate. Star formation cannot be rushed. It proceeds at its own unhurried pace, governed by the fundamental forces of nature working in perfect harmony. A star like our Sun takes about 50 million years to fully form from its first gravitational contraction to its debut as a full-fledged, fusion-powered star. Larger stars form more quickly, while smaller ones take even longer, a patience beyond human comprehension. As you continue to relax, imagine the gentle processes occurring within these cosmic clouds, the slow drift of particles, the gradual accumulation of matter, the patient waiting as gravity does its work over eons. Here is a reminder that some of the most beautiful and important processes in our universe cannot be rushed, but unfold in their own time, guided by natural forces working in perfect balance. In stellar nurseries, we find a profound metaphor for growth and transformation. The idea that from diffuse beginnings, with time and the right conditions, remarkable new creations can emerge. As you drift toward sleep, Let the peacefulness of these cosmic cradles remind you of the value of patience, of quiet development, and of the beauty that comes from natural processes unfolding in their own perfect time. As we journey deeper into the cosmos tonight, let's widen our view beyond individual nebulae to consider the vast island universes that house them, galaxies. These immense cosmic cities, each containing billions upon billions of stars, represent the next level in the hierarchy of structure in our universe. As you relax and prepare for sleep, allow yourself to contemplate the serene majesty of these distant stellar metropolises. Galaxies come in several main types, each with its own tranquil beauty and unique characteristics. The most recognizable are spiral galaxies, with their elegant pinwheel structures spinning slowly through the void. Our own Milky Way is a spiral galaxy, though we cannot see its full shape from our position within one of its arms. Spiral galaxies are characterized by flat disks with graceful arms winding outward from a central bulge, like cosmic hurricanes frozen in time and space. These spiral arms aren't solid structures, but rather waves of star formation moving through the galactic disk, similar to how a sound wave moves through air without carrying the air molecules along with it. Stars pass in and out of spiral arms over billions of years, but the arms themselves maintain their shape through the delicate physics of density waves. As these waves pass through regions rich in gas and dust, they gently compress the material, triggering the formation of new stars like ripples moving across a cosmic pond. The most luminous parts of spiral arms are the hot, bright, short-lived stars that form within them. These massive stars, living fast and dying young by cosmic standards, illuminate the surrounding gas clouds, creating the distinctive bluish glow that makes spiral arms visible from enormous distances. Meanwhile, the spaces between the arms contain older, more settled stars, patiently orbiting the galactic center at their own measured pace. In many spiral galaxies, the center contains a bar-like structure extending outward from the central bulge, with the spiral arms beginning at the ends of this bar. These barred spiral galaxies, including our own Milky Way, show how even galaxies can change their structure over immense time periods. The bars are thought to form as stars in roughly circular orbits gradually shift to more elongated paths, creating a radial structure that helps channel gas toward the galactic center, feeding star formation or even central black holes. The central bulges of spiral galaxies tell their own quiet stories. These roughly spherical regions contain mostly older, redder stars moving in more chaotic orbits compared to the orderly rotation of the disk. Many bulges harbor supermassive black holes at their very centers, objects of extraordinary gravity that, despite their reputation, mostly exist in peaceful harmony with the stars around them. Our own galactic black hole, Sagittarius A, quietly rests at the heart of the Milky Way, its presence detected only by its subtle gravitational influence on nearby stars. In stark contrast to the flat disks of spiral galaxies are the elliptical galaxies, cosmic clouds of stars with shapes ranging from nearly spherical to elongated ellipsoids. These galaxies lack the organized structure of spirals, with no disk or spiral arms. Instead, their stars move in random orbits around the galactic center, like bees around a hive with no organized flight pattern. This gives elliptical galaxies their smooth, featureless appearance when viewed through telescopes. Elliptical galaxies tend to contain older stellar populations than spirals, with relatively little gas or dust remaining for new star formation. Their stars are predominantly older, cooler, and redder than the young blue stars that illuminate spiral arms. In the language of astronomers, elliptical galaxies are often described as red and dead, though this terminology belies their quiet beauty and stability. Some of the largest galaxies in the universe are giant ellipticals, containing trillions of stars and spanning millions of light years. The formation history of elliptical galaxies is written in their structure. Many are thought to be the result of galaxy mergers, the slow-motion collisions between spiral galaxies that transform their organized disks into more chaotic elliptical forms. These mergers happen over billions of years, so gradually that from a human perspective, they would appear nearly motionless. The stars within merging galaxies rarely collide with each other. The spaces between them are so vast that they typically pass by one another like ships in the night. But the overall structures of the galaxies are transformed by their mutual gravitational dance. Between the spirals and ellipticals lie the lenticular galaxies, sometimes called S0 galaxies, transitions between the two main types. Lenticular galaxies have the disk shape of spirals but lack their distinctive arms. They contain mostly older stars like ellipticals, suggesting they may be spiral galaxies that have used up or lost most of their star-forming gas and dust. These galaxies demonstrate how even cosmic structures evolve over time, transitioning from one form to another as their stellar populations age and their gas content changes. Not all galaxies fit neatly into these categories. Irregular galaxies defy classification with their asymmetric, often chaotic appearances. Some irregulars are the results of gravitational disturbances from nearby galaxies, while others may be dwarf galaxies with too little mass to organize themselves into more regular structures. The large and small Magellanic Clouds, satellite galaxies of our Milky Way visible from the southern hemisphere, are examples of irregular galaxies that orbit our own. The forces that shape these vast cosmic cities operate on scales almost beyond comprehension. Gravity, the weakest of the fundamental forces on the particle scale, becomes the dominant architect at galactic scales. It holds billions or trillions of stars in their orbits around the galactic center, maintains the structure of spiral arms through density waves, and drives the slow-motion mergers that create elliptical galaxies. Yet gravity alone cannot explain the behavior of galaxies. Observations of how galaxies rotate reveal that they contain far more mass than can be accounted for by their visible stars, gas, and dust. This invisible component, making up about 85% of a galaxy's mass, is what astronomers call dark matter. Though we cannot see it directly, its gravitational effects are unmistakable, forming a vast, spherical halo around each galaxy that extends far beyond the visible stars. The mysterious dark matter, whatever its true nature, plays a crucial role in the peaceful stability of galaxies. Without it, the rapid rotation observed in the outer regions of spiral galaxies would cause them to fly apart. Instead, the dark matter's gravitational embrace holds everything together in a cosmic balance that has maintained galactic structures for billions of years. As you continue to relax, consider the profound tranquility of these galactic systems. Despite containing hundreds of billions of stars, countless nebulae, and complex gravitational interactions, galaxies maintain their structures over timescales that dwarf human existence. Our Sun has orbited the center of the Milky Way just 20 times since its formation, 4.6 billion years ago, each orbit taking about 230 million years to complete. The stars that make up these galactic cities are themselves mostly separated by vast gulfs of empty space. The average distance between stars in our galactic neighborhood is about 5 light-years, a journey that would take our fastest spacecraft tens of thousands of years to traverse. This emptiness is part of what allows galaxies to be such stable, enduring structures. Like a well-designed building with room for movement, the spaces between stars allow them to adjust their orbits gradually in response to gravitational influences without catastrophic collisions. In your mind's eye, picture these majestic cosmic structures, the elegant spiral arms of galaxies like the whirlpool or pinwheel, slowly turning in the darkness, the smooth, luminous forms of elliptical galaxies like M87 containing the collective light of trillions of suns. The transitional, lenticular galaxies, neither spiral nor elliptical, but beautiful in their in-between state. Each represents a different path in galactic evolution, a different expression of how matter can organize itself under the patient guidance of fundamental forces. As your consciousness drifts among these island universes, remember that what appears chaotic at one scale reveals its order at another. The seemingly random position of stars conceals the elegant structure of galaxies. The apparently haphazard distribution of galaxies themselves forms part of a vast cosmic web, with galaxy clusters strung along filaments of dark matter stretched across the universe. Even in the greatest apparent disorder, patterns and harmonies emerge when viewed with the right perspective, a comforting thought to carry into peaceful sleep. As we continue our tranquil journey through the cosmos, let us turn our attention homeward to explore our own celestial abode, the Milky Way galaxy. This vast spiral of stars, gas, and dust has cradled our solar system for billions of years, its gentle rotation carrying us around the galactic center with patient constancy. On a clear night, far from city lights, you can observe the Milky Way as a misty band of light stretching across the sky. This hazy glow represents the combined light of billions of stars too distant to be distinguished individually by the naked eye. What we're seeing when we look at this band is the disk of our galaxy from within, like looking at a forest while standing among the trees, unable to see its full extent or true shape. Our Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure composed of stars from which the spiral arms extend. It measures approximately 100,000 light-years in diameter, a distance so vast that light, traveling at 186,000 miles per second, would take 100,000 years to cross from one side to the other. Within this enormous cosmic structure, our solar system resides in a relatively quiet neighborhood called the Orion Arm, about 27,000 light-years from the galactic center. The disk of our galaxy, where the spiral arms reside, is remarkably thin compared to its diameter, only about 1,000 light-years thick. Above and below this disk extends the galactic halo, a spherical region of older stars and globular clusters that envelops the entire galaxy. Within this halo lies an even larger sphere of invisible dark matter, whose gravitational influence helps hold our galaxy together. At the very heart of our Milky Way lies a supermassive black hole named Sagittarius A, pronounced Sagittarius A star. With a mass of about 4 million suns compressed into a region smaller than our solar system, this cosmic giant exerts a powerful gravitational influence on the stars in the central bulge. Yet despite its enormous mass, Sagittarius A is currently in a dormant phase, consuming very little matter and existing in peaceful harmony with the stars that orbit around it. Our galaxy rotates, but not like a solid wheel. Stars closer to the center complete their orbits more quickly than those farther out, creating a differential rotation that would eventually wind the spiral arms too tightly were it not for density waves that maintain their structure. Our Sun, along with its planets, takes about 230 million years to complete one orbit around the galactic center, a period sometimes called a cosmic year. Since its formation 4.6 billion years ago, our solar system has completed about 20 such orbits, traveling through different regions of the galaxy, but always remaining within the quiet neighborhood of the Orion Arm. The Milky Way contains between 100 and 400 billion stars, each a sun in its own right, many with planetary systems of their own. Recent studies suggest there may be more planets than stars in our galaxy, with potentially billions of Earth-sized worlds orbiting within the habitable zones of their parent stars. Among all these stars, our Sun is fairly typical, a G-type main sequence star of intermediate age, neither among the largest nor the smallest, neither the youngest nor the oldest. Beyond individual stars, our galaxy contains about 150 globular clusters, densely packed spherical collections of hundreds of thousands of older stars that orbit the galactic center like satellites. It also houses thousands of open star clusters, looser groupings of younger stars born from the same nebula. Our Sun may have formed in such a cluster, but has since drifted away from its stellar siblings as they all follow their individual paths around the galaxy. The spiral arms of the Milky Way are not physical structures, but rather density waves, regions where stars and gas are temporarily compressed, triggering new star formation. The compression causes clouds of gas and dust to collapse, giving birth to new stars, whose bright but brief lives illuminate the spiral arms before they burn out. Meanwhile, older stars pass through the arms unaffected, like cars moving through a traffic jam before continuing on their way. Our galaxy's 4 major spiral arms are named the Norma arm, the Scutum Centaurus arm, the Sagittarius arm, and the Perseus arm. Our solar system resides in a smaller arm called the Orion arm, or local spur, which is situated between the Sagittarius and Perseus arms. These arms contain the majority of the galaxy's ongoing star formation, their gases compressed by the passage of density waves to create the conditions necessary for new stars to form. The Milky Way is rich in interstellar matter, the gas and dust that fills the space between stars. This material consists primarily of hydrogen gas, with smaller amounts of helium and trace quantities of heavier elements. Denser clouds of this material form nebulae, the cosmic nurseries where new stars are born. Our galaxy contains thousands of such nebulae, many visible through even amateur telescopes as fuzzy patches of light or dark silhouettes against brighter backgrounds. Our home galaxy doesn't exist in isolation, but is part of a small collection of galaxies called the Local Group. This galactic neighborhood includes the large Andromeda galaxy, similar in size to the Milky Way, as well as the smaller Triangulum galaxy, and dozens of dwarf galaxies. Many of these smaller galaxies orbit the Milky Way as satellites, including the large and small Magellanic Clouds visible from the southern hemisphere as detached pieces of the Milky Way's band. As you rest and prepare for sleep, consider your place within this vast cosmic structure. Our Sun, one star among billions, orbits the galactic center at about 515,000 miles per hour. Earth orbits the Sun at about 67,000 miles per hour. And yet, despite these enormous speeds, the vastness of space makes these movements feel imperceptible. There is no sensation of rushing or hurry, only the steady, patient rotation that has continued for billions of years and will continue for billions more. The perspective offered by our galaxy can be deeply calming. The concerns that seem so urgent in daily life fade when viewed against the backdrop of 100 billion stars, each with its own history, many with their own planets, all moving in their measured orbits through the cosmic dance of gravity. The Milky Way has witnessed the entire history of humanity as less than a moment in its long existence, a reminder of how brief our troubles are in the grand context of time. From our position within the Milky Way, we can see only a fraction of its true majesty. But through the patient work of astronomers, we've pieced together an understanding of our galactic home that reveals its quiet splendor. Like a vast cosmic garden, the Milky Way nurtures stars from birth to death, recycles their materials through nebulae, and maintains an environment where planets can form and life can emerge. At least in one instance that we know of, and perhaps in many others yet to be discovered. As you drift toward sleep, imagine yourself floating gently above the galactic disk, seeing the spiral arms unfurled below like cosmic petals, studded with the lights of billions of stars in all stages of life. From this perspective, the galaxy's slow rotation becomes visible, a majestic turning that carries each star along its predestined path, including the small yellow star that gives light to Earth and the other planets of our solar system. In this vision of cosmic harmony, find the peace that comes from being part of something vast, beautiful and enduring. Our home galaxy, the Milky Way. As we continue our tranquil journey through the cosmos, let us turn our gaze beyond the boundaries of our own galaxy to its nearest large neighbor, the majestic Andromeda Galaxy. Known to astronomers as Messier 31 or M31, this spiral beauty holds a special place among the celestial wonders visible from Earth. On clear, moonless nights, far from city lights, Andromeda appears to the naked eye as a small, fuzzy patch in the constellation that shares its name. The only galaxy beyond our own that most people will ever see without optical aid. This faint smudge of light belies Andromeda's true nature. At approximately 2.5 million light-years from Earth, the light we see tonight left this neighboring galaxy when our earliest human ancestors were just beginning to walk upright in Africa. Despite this vast distance, Andromeda stretches across 220,000 light-years, making it significantly larger than our own Milky Way. If we could see Andromeda's full extent in our night sky, it would appear 6 times wider than the full moon. A truly breathtaking sight, if human eyes were sensitive enough to detect its faint outer regions. Like our own galaxy, Andromeda is a spiral, with graceful arms winding outward from a bright central bulge. Also like the Milky Way, it possesses a central bar structure, classifying it as a barred spiral galaxy. Its disk contains between 800 billion and 1 trillion stars, potentially twice as many as our home galaxy, all orbiting around a central supermassive black hole estimated to be 100 million times more massive than our Sun. Andromeda shares many characteristics with our Milky Way, like cosmic siblings with similar appearances but unique personalities. Both galaxies have spiral structures, both contain vast amounts of interstellar dust and gas, and both are surrounded by hundreds of globular clusters, dense collections of ancient stars that orbit their host galaxies like tiny satellites. Andromeda even has its own system of satellite galaxies, including M32 and M110, which are often visible in the same telescope field of view as their massive parent. One of the most serene aspects of contemplating Andromeda is considering its patient approach toward our own galaxy. Andromeda and the Milky Way are moving toward each other at approximately 110 kilometers per second, about 250,000 miles per hour. Despite this seemingly rapid pace, the vast distance separating the two galaxies means their eventual meeting lies about 4.5 billion years in the future, roughly the same amount of time that has elapsed since Earth formed. This approaching collision, more accurately described as a merger, will unfold with cosmic gentleness. When Andromeda and the Milky Way begin to interact, their mutual gravitational attraction will distort their elegant spiral structures, drawing out long tidal tails of stars and gas. The two galaxies will pass through each other, then be pulled back together, oscillating like soft pendulums before settling into a single, larger elliptical galaxy that astronomers have already named Milkomeda, or Andromeda Way. Despite the enormous energies involved in this galactic merger, the vast distances between individual stars mean that actual stellar collisions will be exceptionally rare. Our Sun and its planets, including Earth, are unlikely to collide with any Andromedan stars during the merger. Instead, our solar system will likely be gravitationally repositioned to a different orbit within the newly formed galaxy. By that time, however, our Sun will be nearing the end of its life, having expanded into a red giant that may have already engulfed the inner planets. The night sky visible from Earth will undergo dramatic changes as the merger progresses. As Andromeda approaches over billions of years, it will grow progressively larger in our sky. About 3.9 billion years from now, Andromeda will fill the night sky, its spiral structure clearly visible even without telescopes. The merger itself will transform the sky into a chaotic but beautiful dance of stars as the two galaxies pass through each other and their structures begin to intermingle. Today, astronomers study Andromeda not only as our future partner, but as a window into a galaxy very much like our own, but with a unique perspective. Because we observe Andromeda from outside, we can see its full structure in a way we cannot observe the Milky Way. This external view helps scientists better understand spiral galaxy dynamics and evolution, making Andromeda a valuable cosmic laboratory. Andromeda's stellar population tells its own tranquil story. The galaxy contains stars of all ages, from ancient red giants that formed billions of years ago to hot, young blue stars that recently ignited in its spiral arms. Astronomers have identified hundreds of thousands of individual stars within Andromeda using powerful telescopes like Hubble, each one a sun in its own right, potentially with its own family of planets. The galaxy's spiral arms, like those of the Milky Way, are not fixed structures, but density waves, regions where stars and gas temporarily cluster together, compressing interstellar material and triggering new star formation. These waves move through the galaxy like ripples on a pond, with individual stars moving in and out of the arms as they orbit the galactic center. This creates the beautiful spiral pattern we observe, illuminated primarily by the bright, short-lived stars that form within the compressed gas of the arms. Andromeda's central region houses a complex structure. At its very heart lies a supermassive black hole surrounded by a double nucleus, an unusual feature that astronomers believe may be the result of a past merger with a smaller galaxy. This central region also contains a large population of older stars that give it a yellowish or reddish appearance compared to the bluer spiral arms where younger stars predominate. Like our Milky Way, Andromeda is surrounded by a vast halo of dark matter that extends far beyond its visible stars. This invisible material, detectable only through its gravitational effects, makes up about 90% of the galaxy's total mass and plays a crucial role in determining its structure and evolution. The dark matter halos of Andromeda and the Milky Way are already beginning to interact, their gravitational influence reaching far beyond the visible galaxies. As you relax and prepare for sleep, consider the peaceful journey of light from Andromeda to your eyes. The photons reaching Earth tonight have traveled through intergalactic space for 5 million years, passing through the vast emptiness that separates galaxies. They set out long before human civilization began, and have continued their unwavering path at the speed of light until this moment, when they complete their journey by striking your retina, connecting you directly to this distant galaxy. In contemplating Andromeda, we find a beautiful reminder of cosmic companionship. Our Milky Way is not alone in the universe, but exists alongside other majestic galaxies, some similar, some vastly different, all part of the greater cosmic structure. There is a gentle comfort in knowing that even galaxies do not travel through the universe in isolation, but move in relationship with their neighbors, sometimes coming together to create new, blended structures that carry forward the stories of their component parts. Ciao. As your consciousness drifts toward sleep, imagine the slow, stately approach of Andromeda and the Milky Way, two majestic spirals gradually moving toward their distant embrace. In this cosmic dance, choreographed by gravity over billions of years, find a peaceful perspective on change and transformation. Even galaxies, the largest coherent structures of visible matter in the universe, are not eternal in their current forms, but evolve and merge, creating new patterns while preserving the stars that make them shine. As you continue to relax and prepare for sleep, let's immerse ourselves in one of the most enchanting aspects of nebulae, their breathtaking colors. These cosmic clouds paint the canvas of space with hues that range from delicate pinks and vibrant reds to cool blues and subtle greens, creating celestial artworks that have captivated humans since we first pointed telescopes toward the heavens. The colors we observe in nebulae tell us much about their composition and the processes occurring within them. Unlike the colors of a sunset or a flower, which come from pigments that absorb some wavelengths of light and reflect others, nebular colors are produced primarily by the emission of light from excited atoms and the scattering of starlight by cosmic dust. Hydrogen, the most abundant element in the universe, contributes the most recognizable color to emission nebulae, a warm, rosy red. When ultraviolet light from hot, young stars strikes hydrogen atoms, it energizes their electrons, temporarily boosting them to higher energy states. As these electrons eventually fall back to their normal positions, they release the excess energy as light. For hydrogen, this often produces a specific wavelength of red light, known as H-alpha, with a wavelength of 656.3 nanometers. This creates the dominant reddish glow visible in famous nebulae like the Orion Nebula, the Lagoon Nebula, and the North America Nebula. Oxygen, though far less abundant than hydrogen, produces some of the most striking colors in nebulae. When doubly ionized, having lost 2 electrons, oxygen emits a vivid blue-green light. This distinctive teal color is particularly prominent in planetary nebulae, the shells of gas expelled by dying stars. The Ring Nebula and the Cat's Eye Nebula showcase this beautiful aquamarine hue, creating celestial gemstones that shine against the black velvet of space. Nitrogen contributes subtle but important hues to the nebular palette. When ionized, nitrogen atoms emit light primarily in the red portion of the spectrum, but at different wavelengths than hydrogen. This creates variations in the red tones of emission nebulae, adding depth and complexity to their appearance. In nebulae with significant nitrogen content, photographers using specialized filters can distinguish these different sources of red light, revealing additional structural details that might otherwise be missed. Sulfur, when ionized, produces another shade of red light, slightly deeper than hydrogen's characteristic emission. In composite images made with narrowband filters, astronomers often assign this sulfur emission to the red channel, hydrogen to green, and oxygen to blue, creating what are called Hubble palette images, with dramatic, sometimes psychedelic color schemes that enhance subtle differences in nebular composition and temperature. The beautiful blues seen in reflection, nebulae come from an entirely different process. Rather than emitting their own light, these nebulae contain dust particles that reflect and scatter the light from nearby stars, similar to how our daytime sky scatters sunlight. Small dust particles scatter blue light more efficiently than red, the same reason our Earth's sky appears blue, giving reflection nebulae like those surrounding the Pleiades star cluster their characteristic azure glow. Dark nebulae, in contrast, appear as silhouettes against brighter backgrounds. These clouds contain dust particles that absorb and block light, creating striking shapes like the famous Horsehead Nebula in Orion or the flowing tendrils of the Elephant's Trunk Nebula. Though they appear black or dark brown, these nebulae are not colorless. If illuminated from the side, they would display colors similar to reflection nebulae. Their darkness comes from their position relative to our line of sight, blocking the light of more distant stars. The color variations we observe in nebulae reveal temperature differences within these vast clouds. Hotter regions where intense star formation is underway often display the energetic blues and greens of ionized oxygen, while cooler regions show the more subdued reds of hydrogen and nitrogen. These temperature gradients create the complex, variegated appearance of large nebulae, where different processes occur simultaneously in different regions. When we look at photographs of nebulae, It's important to remember that many of the most spectacular images are enhanced to reveal details our eyes could never see directly. Human color vision works poorly in dim light, which is why nebulae appear mostly grayish when observed visually through telescopes. Cameras, however, can collect light over long exposures and detect wavelengths beyond human perception, including ultraviolet and infrared. Astronomers then assign colors to these different wavelengths, sometimes using natural color schemes that approximate what the human eye might see if it were more sensitive, and sometimes using false color to highlight particular features or chemical compositions. In the Hubble Space Telescope's famous Pillars of Creation image of the Eagle Nebula, for instance, the golden-brown colors represent regions rich in hydrogen and nitrogen, while the bluish areas indicate the presence of oxygen. This color coding helps astronomers understand the nebula's composition and the processes shaping these towering columns of gas and dust. The colors of nebulae change very slowly over time as stars form within them, ionize their surroundings, and eventually disperse the remaining gas with their stellar winds. A nebula might maintain its general appearance for thousands or even millions of years, but on cosmic timescales, these structures are as ephemeral as clouds in Earth's sky. The colors we observe are like snapshots of ongoing processes, brief moments in the long life cycle of matter in our universe. As you continue to relax, imagine the delicate processes creating these colors throughout our galaxy. In countless nebulae, from the famous ones that have been photographed in detail to the many more that remain unobserved, atoms are constantly absorbing energy from starlight and releasing it again as the specific wavelengths that create nebular colors. Gas clouds are being compressed to form new stars, while aging stars are shedding their outer layers to form new nebulae. The palette of nebular colors represents an ongoing cycle of stellar birth, life, and death, a cosmic art constantly in the making. The colors we see in nebulae connect us directly to the atomic processes that govern our universe. The same electron transitions that create a hydrogen atom's distinctive red emission in a distant nebula operate in the atoms that make up our own bodies. The oxygen that gives planetary nebulae their blue-green glow is chemically identical to the oxygen we breathe. In observing nebular colors, we're witnessing the same fundamental physics that enables all life on Earth, expressed on a vast cosmic canvas. As your thoughts drift among these colorful cosmic clouds, allow yourself to feel a connection to these distant yet fundamentally related phenomena. The peaceful progression of energy through atoms, creating light of specific colors, the gentle scattering of starlight by cosmic dust, the patient accumulation of these effects over vast regions of space to create the nebular tapestries we observe, all remind us of the underlying order and harmony of natural processes, operating the same way, whether across light years or within our own bodies. Let the tranquil beauty of nebular colors carry you toward restful sleep, your mind filled with visions of delicate pinks, subtle blues, and luminous teals painted across the cosmic canvas. In these colors, find both the wonder of distant astronomical processes and the comfort of connecting with the larger universe of which we are all an integral part. As you drift deeper into relaxation, let's explore the profound harmony that maintains the structure of galaxies across cosmic time. These vast stellar cities, containing hundreds of billions of stars, operate according to principles that balance competing forces with exquisite precision, creating stable structures that can persist for billions of years. At the heart of galactic harmony lies the force of gravity, the silent architect that shapes the cosmos at its largest scales. In galaxies, gravity performs a delicate balancing act. It must be strong enough to bind together billions of stars into a coherent structure, yet gentle enough to allow those same stars to maintain their orbits rather than collapsing toward the center. This balance creates the graceful spiral patterns and stately elliptical forms that define galactic structures. Each star within a galaxy follows its own orbital path around the galactic center, guided primarily by the combined gravitational influence of all other stars, gas, dust, and dark matter. Yet, despite the complexity of these countless gravitational interactions, galaxies maintain remarkably stable structures over billions of years. In our Milky Way, stars in the neighborhood of our Sun complete one orbit around the galactic center approximately every 230 million years, a period astronomers sometimes call a cosmic year. The orbits of stars are not perfect circles, but ellipses of varying eccentricity. Stars closer to the galactic center complete their orbits more quickly than those farther out, creating what astronomers call differential rotation. In spiral galaxies, this differential rotation would eventually wind the spiral arms too tightly, destroying their pattern, if not for the influence of density waves that help maintain their structure. These density waves move through the galactic disk, much like sound waves move through air or water waves across the ocean. As these waves pass through regions rich in gas and dust, they compress the material slightly, triggering star formation. The brightest stars that form in these compressed regions are massive but short-lived, shining brilliantly for just a few million years before exhausting their fuel. These bright stars illuminate the spiral arms, making them visible against the background of older stars that populate the entire galactic disk. Individual stars pass through the spiral arms as they orbit the galaxy, like cars moving through a traffic jam, but the pattern itself persists. The central bulges of spiral galaxies tell another story of cosmic harmony. These roughly spherical concentrations of older stars move in more complex orbits, creating a three-dimensional structure, unlike the flatter disk where spiral arms reside. In many galaxies, including our own Milky Way, the central bulge contains a supermassive black hole whose mass correlates closely with the properties of its host galaxy, a relationship astronomers have observed but still don't fully understand. Despite their enormous gravitational influence, these central black holes coexist peacefully with the stars around them, actively consuming matter only occasionally when gas or stars venture too close to their event horizons. Elliptical galaxies, lacking the organized rotation of spirals, maintain their structure through different harmonies. Their stars move in random orbits around the galactic center, creating a three-dimensional ellipsoidal shape that can range from nearly spherical to highly elongated. The distribution of orbits in various directions prevents the galaxy from collapsing, creating a stable configuration that can persist with little change for billions of years. Many elliptical galaxies are believed to be the results of mergers between spiral galaxies, their final form representing a new equilibrium reached after the gravitational disturbances of the merger have settled. The vast majority of a galaxy's volume consists of nearly empty space. Stars, despite their abundance, are separated by distances thousands of times greater than their diameters. Even in the densest regions of galaxies, direct collisions between stars are extraordinarily rare. This spaciousness is part of what allows galaxies to be such stable structures. Stars have room to adjust their orbits in response to gravitational influences without disruptive collisions. Yet visible matter, stars, gas, and dust, tells only part of the story of galactic harmony. Observations of how galaxies rotate reveal that they contain far more mass than can be accounted for by what we can see. This invisible component, called dark matter, makes up about 85% of a galaxy's mass and forms a vast, roughly spherical halo that extends far beyond the visible stars. The gravitational influence of this dark matter is essential for maintaining galactic structure, particularly in the outer regions of spiral galaxies, where stars orbit faster than they should if only visible matter were present. The relationship between dark matter and visible matter creates another level of galactic harmony. Computer simulations suggest that galaxies form within massive halos of dark matter, which provide the gravitational scaffolding around which ordinary matter coalesces. As gas falls into these dark matter halos and cools, it forms stars and gives rise to the luminous galaxies we can observe. Though we still don't know exactly what dark matter is composed of, its gravitational effects work in concert with normal matter to create and maintain galactic structures. Within this grand galactic ballet, smaller harmonies play out continuously. Star clusters, both the dense, ancient globular clusters in the galactic halo and the looser, younger open clusters in the disk, represent miniature gravitational systems where dozens to millions of stars orbit their common center of mass. Giant molecular clouds, the birthplaces of new stars, maintain their structure through a balance between gravity, gas pressure, turbulence, and magnetic fields until parts of them collapse to form new stars. Even the solar systems within galaxies represent harmonies of gravitational balance. Our Sun, like many stars, is orbited by planets whose paths have been stabilized over billions of years. These planetary systems themselves are shaped by the larger galactic environment. The Sun's journey around the Milky Way occasionally brings it closer to other stars or through regions of slightly higher density, which may disturb the outermost regions of our solar system while leaving the inner planets undisturbed. The interstellar medium, the gas and dust between stars, participates in its own harmonious cycles. When stars form from collapsing clouds of gas, the most massive among them live brief but brilliant lives before exploding as supernovae. These explosions return enriched material to the interstellar medium, seeding it with heavier elements forged in stellar cores and during the explosive process itself. This recycled material eventually becomes part of new stars and planetary systems, continuing a cycle that has progressively enriched galaxies with elements heavier than hydrogen and helium over cosmic time. Magnetic fields, often overlooked in discussions of galactic structure, extend throughout galaxies and help regulate the behavior of ionized gas and cosmic rays. These fields are typically thousands of times weaker than Earth's magnetic field, yet they influence processes like star formation and the propagation of high-energy particles throughout the galaxy. In spiral galaxies, magnetic field lines often follow the spiral arms, creating another layer of structure that works in concert with gravity and rotation. The peaceful harmony of galaxies extends to their interactions with one another. Galaxies frequently pass near each other in space, their mutual gravitational attraction causing distortions in their structures. These interactions can draw out long tidal tails of stars and gas, create bridges of material between galaxies, or trigger bursts of star formation, where compressed gas collapses to form new stars. Over billions of years, galaxies may merge completely, their stars and gas combining to form a single, larger galaxy. Despite the enormous energies involved, these processes unfold with cosmic gentleness, their effects only becoming apparent over millions or billions of years. As you continue your journey toward restful sleep, consider the profound implications of this galactic harmony. The delicate balance of forces that maintains galaxies, gravity, rotation, pressure, magnetism, creates stable environments where stars can orbit for billions of years, planets can form around those stars, and life can potentially emerge and evolve on those planets. Our own existence depends on the stability provided by these cosmic harmonies, which have maintained our galactic home long enough for life to develop and for humans to evolve the consciousness with which we now contemplate the universe. In the grand tapestry of galactic harmony, we find a metaphor for the balance we seek in our own lives, not perfect stillness, but dynamic equilibrium, where opposing forces create stability through their interaction. Just as galaxies maintain their structure despite the constant motion of their component stars, we might find our own sense of peace, not in the absence of activity, but in the balanced flow of energies that sustains us. As your consciousness drifts among these thoughts of cosmic harmony, allow yourself to feel part of this great, ordered universe, a universe where even structures as vast as galaxies find their perfect balance and maintain it across eons of time. In this perspective, find the peace that comes from connecting with something far greater than daily concerns, something whose patient rhythms have continued for billions of years and will continue for billions more. As you settle more deeply into relaxation, let's explore one of the most profound processes in our universe, the continuous cycle of cosmic recycling that connects stars, nebulae, planets, and even the atoms in your body. This grand cycle represents nature's ultimate form of renewal, where nothing is truly lost, but instead transformed from one state to another across billions of years. When we look up at the night sky, we're seeing stars in various stages of life, from young, hot stars just beginning their journeys to ancient stars nearing their end. What may not be immediately apparent is that these stars represent different generations in a continuous lineage of matter, each generation enriching the cosmos with new elements that become part of future stars, planets, and eventually, life itself. Our cosmic recycling story begins shortly after the Big Bang, some 13.8 billion years ago. In those first moments, the universe contained primarily the simplest elements: hydrogen, helium, and traces of lithium. All the other elements that make up our world, the carbon in our cells, the oxygen we breathe, the calcium in our bones, were yet to be created. These elements would be forged through the patient processes of stellar evolution and cosmic recycling. The first generation of stars formed from these primordial elements, drawing together clouds of hydrogen and helium through gravity's gentle pull. These early stars were often massive and short-lived compared to stars like our Sun. Without heavier elements to help radiate away energy during formation, many of these first stars grew to enormous sizes, perhaps hundreds of times the mass of our Sun. Within the cores of these first stars, nuclear fusion combined hydrogen atoms to form helium, releasing the energy that made the stars shine. In more massive stars, after the hydrogen in the core was exhausted, temperatures and pressures became high enough to fuse helium into carbon, and then carbon into oxygen, neon, and heavier elements, up to iron in the most massive stars. Each fusion reaction released energy while building more complex atomic nuclei, step by step. But iron represents a turning point in stellar nucleosynthesis. Fusing iron atoms consumes rather than releases energy, so once a massive star develops an iron core, fusion can no longer provide the outward pressure needed to counterbalance gravity. When this happens, the star's core collapses in seconds, and the resulting rebound creates a supernova explosion, one of nature's most energetic events. In the extreme conditions of a supernova, something remarkable happens. The tremendous energies involved enable the creation of elements heavier than iron, including silver, gold, platinum, and uranium, through a process called rapid neutron capture. In a brief but intense moment, atomic nuclei are bombarded with neutrons faster than they can decay, building increasingly heavy elements. These newly forged atoms are then scattered into space by the force of the explosion. Less massive stars, like our Sun, contribute to cosmic recycling in a gentler way. As they exhaust the hydrogen in their cores, they expand into red giants and begin fusing helium into carbon and oxygen. Eventually, they shed their outer layers in expanding shells called planetary nebulae, releasing these elements into space while their cores contract to form dense stellar remnants called white dwarfs. Yet another recycling pathway involves binary star systems, where one star has already become a white dwarf. If the companion star evolves into a red giant and transfers material to the white dwarf, the dwarf may accumulate enough mass to trigger a thermonuclear explosion called a Type Ia supernova. These consistent and luminous explosions release significant amounts of iron and other elements into interstellar space. Through these various stellar processes, supernovae, planetary nebulae, and stellar winds, the space between stars is gradually enriched with elements heavier than hydrogen and helium. These elements mix with the existing interstellar medium, creating a more diverse chemical environment for the next generation of stars. When new clouds of gas begin to collapse to form second-generation stars, they now contain these heavier elements. Stars like our Sun, born about 4.6 billion years ago, formed from gas clouds already enriched by previous stellar generations. Astronomers can determine that our Sun is at least a third-generation star based on its composition, which includes elements that must have been processed through multiple cycles of stellar birth, life, and death. The cosmic recycling process doesn't stop with stars. As stars form, the surrounding disk of material, enriched with these various elements, provides the building blocks for planets. Rocky planets like Earth condense from the heavier elements, silicon, iron, magnesium, and others, while gaseous outer planets gather primarily hydrogen and helium, along with compounds of carbon, nitrogen, and oxygen. The Earth itself represents a remarkable concentration of elements that were once scattered through interstellar space. The iron in Earth's core, the silicon in its mantle and crust, the oxygen in its atmosphere, all were forged in the hearts of ancient stars that died long before our solar system formed. In a very real sense, our planet is made of stardust, concentrated and transformed through cosmic recycling. This process continues today throughout our galaxy and beyond. In the Orion Nebula, visible on winter nights as a fuzzy patch in Orion's sword, new stars are forming from gas that contains atoms processed through multiple generations of previous stars. In the Crab Nebula, we can observe the expanding remnants of a supernova recorded by Chinese astronomers in 1054 CE, its newly created heavy elements beginning their journey into the interstellar medium, where they may eventually become part of new stars and planets. Perhaps most profound is the connection between cosmic recycling and life itself. The carbon that forms the backbone of organic molecules, the nitrogen that is essential for amino acids and proteins, the oxygen that enables cellular respiration, the phosphorus that is crucial for DNA and energy transfer. All these elements were created inside stars and dispersed through space before becoming incorporated into our living world. As the astrophysicist Carl Sagan famously observed, "We are made of star stuff." This poetic statement expresses a literal truth about cosmic recycling. The atoms in your body have existed for billions of years, taking different forms, perhaps as part of a massive star, then scattered through a nebula, later incorporated into a planet, and eventually becoming part of a living organism. When we look at nebulae and star-forming regions, we're seeing the very processes that created the elements necessary for our existence. Even more remarkable is the continuous nature of this recycling. The atoms that make up your body right now will someday return to the environment, perhaps becoming part of other organisms, or the soil, or the air. On a much longer timescale, when our sun eventually expands into a red giant and sheds its outer layers, some of Earth's material, potentially including atoms that were once part of living beings, will be returned to interstellar space, continuing the cosmic cycle. The recognition of this continuous recycling offers a profound shift in perspective. Nothing in our universe is truly new or truly destroyed. Matter is merely transformed from one state to another. The boundaries between stars, planets, and living beings become more fluid when viewed through the lens of cosmic recycling. We are not separate from the cosmos, but integral participants in its ongoing cycles. In some supernova remnants, astronomers have observed dust forming from the newly created elements, the first step in a process that might eventually lead to new planetary systems. The Crab Nebula, for instance, contains complex dust grains forming in the cooling gas, potentially including compounds similar to those that would later form planets in our own solar system. Planetary nebulae, the colorful shells of gas expelled by dying sun-like stars, showcase cosmic recycling in a particularly beautiful form. The Ring Nebula in the constellation Lyra, the Dumbbell Nebula in Vulpecula, and the Helix Nebula in Aquarius all display the elegant structures formed as dying stars release their outer layers. These nebulae, glowing in colors that reveal their chemical composition, represent nature's way of returning stellar material to the interstellar medium for use in future cosmic creations. Within our own solar system, we find evidence of cosmic recycling in meteorites, fragments of asteroids that occasionally fall to Earth. Some of these meteorites contain tiny grains that formed around other stars before our solar system existed. These pre-solar grains survived the formation of our solar system and have remained unchanged for over 4.6 billion years, carrying direct information about the stars that created them. Certain rare meteorites even contain amino acids, the building blocks of proteins, suggesting that some of the ingredients for life may have been delivered to Earth from space. This raises the possibility that the cosmic recycling process may include the distribution of organic compounds throughout galaxies, potentially seeding multiple worlds with the chemical precursors of life. As you drift toward sleep, consider how cosmic recycling connects you to the universe in the most intimate way possible. The iron in your blood once existed in the core of an ancient star before it exploded as a supernova. The calcium in your bones formed in the nuclear furnaces of stars that died before our solar system was born. The carbon in your cells was created by triple helium fusion in the cores of red giant stars. In this perspective, your body is not something separate from the cosmos, but a temporary arrangement of atoms that have been part of the universe's grand cycle for billions of years. There is a profound peace in recognizing this connection, in understanding that we are not merely observers of cosmic processes, but embodiments of them, brief but conscious collections of atoms that have been recycled through stars and nebulae over the history of our galaxy. As you relax into sleep, imagine the journeys that the atoms in your body have taken to reach their current form, from the centers of ancient stars, through colorful nebulae, into the forming solar system, through Earth's geological processes, into the biosphere, and eventually into the unique pattern that is you. And as you dream, perhaps you'll glimpse the future journeys these same atoms will take after they have been part of you, continuing their endless cosmic recycling through the vast reaches of time and space. As you continue to relax and prepare for sleep, let's journey to the farthest reaches of our observable universe to explore the most distant galaxies, ancient cosmic cities whose light has traveled across billions of light years and billions of years to reach us. These remote galactic worlds offer us not just a glimpse across vast distances, but also a look back in time to when the universe was in its youth. When we observe a nearby galaxy like Andromeda, we see it as it was about 2.5 million years ago, the time it took its light to cross the intervening space. But when we look at the most distant detectable galaxies, we're seeing light that has been traveling for over 13 billion years, more than 90% of the age of the universe itself. These observations provide a serene perspective on cosmic history, allowing us to witness how galaxies have formed and evolved across cosmic time. The most distant galaxies appear to us not as the majestic spirals and ellipticals that populate the nearby universe, but as smaller, more irregular collections of stars. In the early universe, galaxies were still in their formative stages, gradually accumulating mass and organizing themselves into the more structured forms we see in closer cosmic neighborhoods. These youthful galaxies were often rich in gas, experiencing intense bursts of star formation that caused them to shine with a bluish hue from their abundance of hot, young stars. To detect these distant cosmic monuments, astronomers use our most powerful telescopes, including the Hubble Space Telescope and its successor, the James Webb Space Telescope. These remarkable instruments collect the faint light that has been traveling across the cosmos since nearly the dawn of time, revealing galaxies as they appeared when the universe was less than 1 billion years old, a mere fraction of its current age. One of the fascinating discoveries from studying these distant galactic worlds is how the overall star formation rate in the universe has changed over time. Roughly 10 billion years ago, when the universe was about a quarter of its current age, galaxies were forming stars at a much higher rate than they do today. Astronomers sometimes refer to this period as cosmic noon, the peak of star-forming activity across the universe. Since that time, the overall rate of star formation has declined as galaxies have used up available gas, and the universe has continued to expand. The light from these distant galaxies doesn't reach us unchanged. As it travels through the expanding universe, the wavelengths of light are stretched by a phenomenon called cosmological redshift. This causes the light to shift toward the red end of the spectrum, sometimes moving ultraviolet and visible light entirely into infrared wavelengths. The farther away a galaxy is, the greater this redshift effect, requiring specialized instruments that can detect infrared light to study the most distant cosmic objects. When we look at galaxies across different cosmic epochs, we can trace their evolutionary journey. The earliest galaxies were relatively small and irregular, often interacting and merging with one another. Over time, these mergers built up larger galaxies, which gradually settled into the ordered structures we see nearby. Spiral galaxies developed their characteristic disk and arm patterns as their rotation became more organized, while elliptical galaxies formed primarily through the mergers of smaller galaxies. One of the most remarkable discoveries about distant galaxies is that supermassive black holes were already present in the early universe. Quasars, incredibly bright galactic cores powered by actively feeding black holes, have been detected more than 13 billion light-years away, existing when the universe was less than 5% of its current age. How these enormous black holes formed so quickly after the Big Bang remains one of astronomy's most intriguing mysteries. The distribution of distant galaxies reveals the larger cosmic structure in which they exist. Rather than being spread evenly throughout space, galaxies tend to form clusters and superclusters, arranged along filaments with vast cosmic voids between them. This foam-like structure, often called the cosmic web, represents the largest known organization in the universe and has its origins in tiny density fluctuations present in the earliest moments after the Big Bang. As we observe more distant galaxies, we can see this cosmic web in its earlier, less developed state. The contrast between cosmic filaments and voids was less pronounced, and galaxy clusters were still in the process of assembling. Over billions of years, gravity has enhanced these structures, drawing more matter into the dense regions and leaving the voids even emptier. The chemical composition of distant galaxies tells another story of cosmic evolution. The earliest galaxies contained primarily hydrogen and helium, elements created in the Big Bang, with very little of the heavier elements astronomers call metals. As generations of stars lived and died within these galaxies, they gradually enriched their surroundings with heavier elements forged in stellar cores and supernova. When we measure the metal content of galaxies at different distances, we can track this enrichment process across cosmic time. Among the most interesting distant galactic worlds are those caught in the act of merging. Collisions between galaxies were more common in the earlier universe, when galaxies were closer together due to less cosmic expansion and had more erratic orbits. These cosmic collisions, unfolding over hundreds of millions of years, triggered bursts of star formation as gas clouds were compressed, creating brief but brilliant chapters in galactic evolution. The irregular shapes of many distant galaxies reflect these ongoing interactions and mergers. Some distant galaxies appear remarkably massive and mature, despite being observed at a time when the universe was quite young. These precocious galaxies challenge our understanding of how quickly galaxies can form and evolve. Their existence suggests that galaxies can grow more rapidly than some models predict, perhaps through exceptionally efficient star formation or through multiple mergers happening in quick succession. The light from the most distant galaxies carries another kind of information. It has passed through all the intervening space on its journey to our telescopes. By carefully analyzing this light, astronomers can detect the presence of gas clouds that existed between galaxies billions of years ago. These ancient clouds, primarily composed of hydrogen, provide crucial information about the state of the universe during its adolescence and the environment in which early galaxies evolved. As we continue to improve our telescopes and detection methods, we push the frontier of observable galaxies ever further back in time. With each new generation of instruments, we glimpse galaxies that are more distant, and therefore younger, gradually approaching the epoch when the very first galaxies formed. These observations help answer fundamental questions about how quickly galaxies assembled when they began forming stars, and how they have evolved into the mature cosmic cities we see in the nearby universe. The study of distant galaxies reminds us of the profound patience inherent in cosmic evolution. The light reaching us tonight from a galaxy 13 billion light-years away began its journey before our solar system existed, before Earth formed, long before any life appeared on our planet. That light has traveled across nearly the entire observable universe, passing countless other galaxies, traversing vast cosmic voids, neither speeding up nor slowing down, maintaining its steady pace at the universe's absolute speed limit. As you drift toward sleep, consider the tranquil perspective offered by these distant galactic worlds. The light we detect from them tonight will continue its journey past Earth, traveling onward through space. Perhaps, billions of years from now, it will be detected by observers in some distant corner of the cosmos, carrying information about our galaxy along with it, a quiet cosmic conversation conducted across the vast reaches of space and time. In contemplating these distant galaxies, we find a peaceful reminder of our place in the cosmic story. We are observers positioned at a particular moment in time, able to look outward and therefore backward, witnessing different chapters of cosmic evolution simultaneously. The universe reveals its history to us through the light of distant galaxies, allowing us to reconstruct the grand narrative of cosmic evolution from the comfort of our small planet, orbiting an ordinary star, in just one of billions of galaxies scattered across the observable universe. As you settle more deeply into relaxation, let's turn our attention to one of the most profound and peaceful cosmic perspectives ever captured, the Hubble Deep Field images. These remarkable observations revealed something extraordinary about our universe by simply staring patiently into what appeared to be empty space. In December 1995, astronomers directed the Hubble Space Telescope to focus on a tiny patch of sky in the constellation Ursa Major. This region, about the size of a grain of sand held at arm's length, appeared to contain nothing special, just a dark area with few visible stars. For 10 consecutive days, Hubble collected light from this seemingly empty space, creating one of the longest exposures ever taken at that time. When the resulting image was processed and released, it revealed something astonishing. Not emptiness, but a cosmic tapestry containing over 3,000 galaxies of various shapes, sizes, and colors, each containing billions of stars. Some appeared as elegant spirals, others as smooth ellipticals, and many as irregular smudges of light. These weren't nearby galaxies, but incredibly distant ones, some so far away that their light had been traveling for over 12 billion years before reaching Hubble's mirrors. The Hubble Deep Field was revolutionary not for what it showed, but for what it implied. If a random, apparently empty patch of sky contained thousands of galaxies, then the entire sky must contain billions upon billions of them. The universe was far more crowded with galaxies than anyone had imagined, each one a vast island universe containing countless stars and, potentially, planets. In 1998, astronomers conducted a similar observation in the southern hemisphere, creating the Hubble Deep Field South. The results were strikingly similar to the original deep field, confirming that what had been observed wasn't a statistical fluke, but representative of the universe at large. Everywhere we look in sufficient depth, we find a universe teeming with galaxies stretching back to the cosmic dawn. In 2004, astronomers went even further with the Hubble Ultra Deep Field, pointing the telescope at a small region in the constellation Fornax and collecting light for nearly 1,000,000 seconds of exposure time. This revealed even fainter and more distant galaxies, approximately 10,000 in an area smaller than a tenth of the full moon's diameter. Some of these galaxies appear as they were just 400, 800 million years after the Big Bang, when the universe was in its infancy. The most recent iteration, the Hubble Extreme Deep Field released in 2012, combined 10 years of observations to create the deepest portrait of the universe yet. In this image, about 5,500 galaxies are visible, some more than 13 billion light-years away, seen as they were when the universe was only about 500 million years old. The faintest galaxies in this image are 1/10,000,000th the brightness of what the human eye can see. Now, imagine the journey of that starlight. To travel across billions of years and unimaginable distances just to reach our eyes. Each photon you see is a traveler from a distant past, whispering secrets of ancient galaxies and cosmic dawns. Such vast patience in the universe's light, a gentle reminder that some things take time beyond comprehension, and that beauty can be found in waiting. As you drift into sleep, let this cosmic patience soothe you. The slow, steady voyage of starlight across the universe, a light show performed on the grandest stage, timeless and infinite. Rest now in the knowledge that you are bathed in the soft glow of a universe much larger than one could ever dream, and that the stars' journeys never truly end. They just keep shining, waiting for you to notice. So, was that trip across the cosmos everything you hoped for? The universe just shared some of its deepest secrets with you, and I've got countless more to whisper. Subscribe now, and we'll explore even darker, more mysterious corners of space together. Just you, me, and infinite wonder. Don't leave me floating alone out here.